Welcome back again. So in previous classes we have designed Butterworth filter, Chebyshev filters, and we have said like the Chebyshev filter is providing us a higher roll-off on the at the cutoff frequency. So if we are trying to say what is going to be the advantage of taking a Chebyshev filter, it certainly be the order of filter. So, but we need to analyze this problem a little bit more in detail. So, let's consider to solve a similar roll-off. Say suppose you have a filter which is a low-pass filter, and suppose you have this as your cutoff frequency, okay, and then it is having this kind of response. So this is your 0 dB and this is gonna be minus 3, approximately minus 3 dB. Okay, so here is the frequency domain, this is omega. So in case someone tell you about we want to design a filter with a roll-off such that when this omega is equals to this omega, this value, say omega 1, this omega 1 divided by omega c, when it is equals to 1.2, the roll-off from this point to this point, it should have minus 30 dB. So practically what I am saying here is, if we have a higher roll-off, so say suppose this is having certain order, say 9, but if we have a higher roll-off, so this the order gonna be increased from 9 or say maybe increased to certain higher value. So this order, say this is n1, this is n2, so n3 gonna be higher than n2, gonna be higher than n1. Okay, so let's not put a value as a order because we need to calculate these. So there are 3 orders, so this would be like this. So and we have seen like the order of the filter is basically the number of elements we are having in our filter. So suppose if you have a higher order filter with the same roll-off, so that means you are, if you are somehow able to increase the roll-off factor, so you are with the same number of order, you are compacting your design. So this is how the Chebyshev filter is quite interesting, while with the same roll-off in the maximally flat design, we can have a lower order filter with the Chebyshev filter. So the number of the reactive elements would be less. So let's see how much improvement we can get when we use a Chebyshev filter in place of a Butterworth filter. And we have taken this as in one example. We want the roll-off to be minus 30 dB of attenuation at omega upon omega c, which is equals to 1.2. So we have taken this as our decision criteria for a roll-off, and we'll see like how much components and what's the order of filter is required to achieve this roll-off with this transfer function. Okay, so let's solve for this. So if we transform this 30 dB into an equivalent linear scale, so this is gonna be 10 to the power 30 divided by 10. Okay, so this is 0.001. So if we put this value here, 0.001, which is equals to 1 over 1 plus omega upon omega c to the power 2n. So if we solve for this, we can have this going to be multiplied here, okay? So 1.00 plus omega upon omega c to the power 2n, which is equals to 1, and we have this as 1 plus. So 1 plus omega upon omega c to the power 2n is equals to 1 divided by 001. So again we simplify this, 1 plus omega upon omega c to the power 2n, which is 1, 2, 3, it becomes 1000. Solving for this, omega upon omega c to the power 2n, which is equals to 999, because this is going to be here and this is going to be subtracted here, and this is become this. If we take, say, a log, say ln of this, so 2n comes out to be in front, ln of omega upon omega c, this is going to be ln 999. So if we solve this, so for n, this is going to be ln 999 divided by ln omega by omega naught, omega c is taken as 1.2. So if we solve this, so let's see what going to be the answer. So this order comes out to be, there is 1, 2 here, this order comes out to be 16. No, it comes out to be, if we calculate this, this is comes out to be 37.88 divided by 2. So it's coming out to be 18 point something, but we always take integer value, so its order comes out to be 19. So what it signifies, if we want to design this kind of roll-off, we have a Butterworth maximum flat if the order of 19. So we need to have 19 lumped component in this configuration, say 1, 2, 3, 4, and so on and so on for 19th combinations. Okay. So now let's take this as a reference. We have got order as 19. Okay. For Butterworth, so for Butterworth with this roll-off, we have got an order of the filter as 19. Okay. So now if we talk in terms of Chebyshev, so Chebyshev filter certainly have some sort of ripples, so that's basically decides by this factor f naught. So we need to choose which ripple factor we need to design. So let's assume the ripple in the pass band is of the order of 1 dB. Okay. So this f naught is LR divided by 10 minus 1 is defined like this. So what would be the LR value? So let's solve this. So 10 to the power 1 by 10 minus 1. So this f naught comes out to be 0.25. 0.2589. So this f naught we have as this value. Okay. Similarly, if we want to have a certain different ripple passband response, say 0.05 dB. So you need to put that value here and you will have a new f naught. Okay, so this is the first step. The second step is the calculating the function, the Chebyshev function for the omega over omega c, which is greater than 1. So this function is I have already placed here. So let's calculate this transfer function for the same roll-off. So the roll-off, we have also calculated this in terms of h of j omega, that was this one. So let's put this in this equation. So this is equals to this 1 over 1 plus f naught and Tn of omega upon omega c. Okay? For simple values, like how this Tn function is defined in for like the argument which is greater than 1, which is defined like this. So if we put this value here, f naught, so the new definition is cosine of hyperbolic square n cosine of hyperbolic omega upon omega c. Okay? And this is equivalent to this value. So if we solve for this, so we have f naught cosine of hyperbolic square n cosine of hyperbolic inverse omega upon omega c is equals to, so this is going to be 1000, 1000 and 1000 minus 1, 9, 9, 9. Okay? So if we further solve this, this is going to be divided by f naught. F naught we have calculated for a prospective passband ratio. So its value is 0.2589. So if we replace 999 divided by 0.2589. Okay? So if we solve this again, so let's rewrite this equation here. Cosine of hyperbolic square n times cosine of hyperbolic inverse omega by omega c we can take as 1.2, and this value is equals to 999 divided by 0.2587. So let's see what this value is. Cosine of hyperbolic inverse. Cosine of hyperbolic inverse. Hyperbolic cosine inverse of 1.2. This comes out to be 0.622, and this is equals to 999, 0.2587, and this is having an argument of cosine of hyperbolic, cosine of square root. Okay, so let's take a square root on this side. So this become cosine of hyperbolic and multiplied by 0.622, and this is going to be square root of this quantity 2587. So let's solve this quantity first. 999 divided by 0.2587, and let's take a square root. So this quantity comes out to be 62.14141. Okay, so for calculating n, we need to take cosine of hyperbolic inverse of 62.141, and this quantity, if we want to say n gonna be equals to cosine of hyperbolic inverse of 62.141 divided by 0.622. So let's solve this value again. So cosine of hyperbolic inverse of 62.141 divided by 0.622. So this comes out to be 7.7 and something. Okay, and we have seen previously, like if we have any real number, so we can took an integer value which is greater than this value. So n equals to 8. So what we have found here, for designing the same roll-off, which is of 30 dB at certain frequency, okay, and if we want to design a Butterworth filter, so we have an order of filter around 19. Okay, and if with the same consideration, well, assuming the ripple factor is equals to 1 dB, we can design the same roll-off with slightly lower order filter. So how many, like it's just a great improvement. Okay, so the order of filter is now 8, so we have less components in the filter design. Okay, so 1, 2, 3, 4, 5, 6, and if we say 7, 1, 2, 3, 4, 5, 6, 7, and 8. So this is gonna be your filter for n equals to 9. So this is the topology. And if we go for 19, so we need to add 19 of such elements. So mostly, like we have reduced the size of the filter approximately 50%. However, we have a little compromise on the passband performance here. We can further reduce this number based on this f0 value. How we can improve? So suppose this is only 1 dB. If we have a passband ripple factor of 3 dB, say, so if we put 3 dB here, so what gonna be change here? So let's have a 3 dB. So f0 become 10 to the power 3 by 10 minus 1. So this would be so this value will become of 0.995. Okay, so what we have done with this f0, we have divided this value here. Okay, so if we solve this for this, so this gonna be 0.995, and let's see what it gonna 0.999 divided by 0.995. So this comes out to be 1004. Okay. Something like this. Okay, so this quantity, what we are doing with this quantity while calculating the order of the filter, we are taking the square root of this quantity. Okay, so just a small change here. So the square root of this 4 So let's consider up to this accuracy. Okay, let's take the square root of this first. Okay, and then what to do with? We need to calculate the cos hyperbolic inverse of this. So this comes out to be this, and divided by from where this factor is coming, or this not going to be changed because this is from omega by omega c. So divided by 0.622. So this comes out to be 6.6. So if we solve this, and this comes out to be 6.6. So we have further reduced the filter n equals to 7. So this is how this LR comes into the picture. So suppose if we want to have a slightly lower ripple factor, say 0.5 dB, so this is going to increase your order a little bit more on the higher side, and if you want to compromise on the passband, so it can further reduce your order of the filter. So number of elements is basically deciding the order of the filter, so you can minimize your filter, however you have little compromise on the passband performance.